Chapter 13 here, which is gases. So obviously in this chapter, we're going to talk about gases, which is obviously the state of matter where everybody has pretty much broken apart from one another. They're flying around. As they're flying around in the container in which they are contained, the number of collisions basically results in the pressure that we associate with the gases. So let's talk about sort of under normal conditions. And usually when we talk about sort of normal conditions, those are kind of like room temperature sort of conditions. Yeah. Is it 13? 9? Is it 9? 13, I believe. It should be gases. Yeah. I'm going to let you know 9 through 9. Yep. All right. So, we are not going to probably put this one on it since we were not going to finish before next weekend. Whatever was before that. Yeah. After 9. Yeah, just 9. We're just going to do 9. That's it. No, I'm kidding with you. No, we're going to do all the chapters. We'll talk about it at the end. I'll diagram it on the board. It'll be a nice talk. We'll talk about it. So why don't we lecture here for a bit and then we'll talk about the exam. All right. All right. So substances that exist in gases under normal conditions will be usually a pressure of 1 atm. So atm is an atmosphere. It is a unit of pressure that we use a lot. And usually around 25 degrees Celsius is sort of standard temperatures. As you go through chemistry, you'll see a lot of some table sort of figures that you go look up in tables and things like that. And usually the experiments are done under those conditions. Kind of 25 degrees Celsius is the normal temperature. 1 atmosphere if you're doing something with pressure and gases, and 1 molar if you're dealing with something that has to do with solutions. So under these normal conditions, ionic compounds really do not kind of go. Ionic compounds, as we know, are cations and anions, so they are positive and negative guys. They are held together by the really strong electrostatic attraction. And electrostatic attraction, which is basically opposites attract to one another, is really what is considered a intramolecular force. And intramolecular forces are usually really sort of strong forces. They are things like electrostatic attraction between the ions. They're also covalent bonding when we share electrons as well. Since if you take an ionic compound, you're pretty much going to heat the heck out of it. Is it will most likely start to sort of melt before it will do that. And I think we did some earlier experiments where we kind of evaporated off the water and we're left with sort of, and if you continue to heat that salt, it never will really evaporate it. Now, covalent compounds or molecular compounds are a little bit different. Molecular compounds obviously are sharing of electrons. And what happens when we have molecular compounds, we do have certain ones that basically are gases or become gases sort of naturally. Things like carbon monoxide, carbon dioxide, ammonia, CH4 is methane. But a lot of molecular compounds, covalent compounds, are solids or liquids at room temperature. The major difference is it's much easier to convert a sort of molecular compound into the gas phase than it is, say, an ionic compound. And that is because, for example, we take the common example of water. Water is a polar molecule where the oxygen is more, hydrogen is more positive. And what basically holds the two water molecules together is this sort of bonding between the positive and negative, which in this case is what is referred to as hydrogen bonding. And hydrogen bonding is an intermolecular force. And an intermolecular force is really the force that holds one sort of entire molecule together with another. So intermolecular forces are always much weaker than intramolecular forces. If you took one water molecule, by the way, the covalent bonding, the sharing of electrons is also an intramolecular force. And we know just from a very simple example of water that intermolecular forces are much weaker than intramolecular forces, because when you go to heat water, like when you're boiling water for noodles or pasta, it is this bond, the bond between the two water molecules, that actually breaks first, allows these guys to go into the gas phase. If it was opposite and the intramolecular force was weaker, what would happen when you start to heat it is these bonds would break, which wouldn't be so great because you make hydrogen gas and oxygen gas, and that would not be so great if you're trying to make some noodles for dinner. But we do break those sort of intermolecular forces. So the general rule is sort of the stronger the attractive force between molecules, the less likely that the molecules will basically be in the gas phase. That's why a lot of organic molecules, like say methane, propane, butane, these are gases under normal conditions because they are mostly nonpolar, and they're held together by very, very weak intermolecular forces. So they're held together super weak forces between each other, and they're able to go into the gas phase relatively easy. So some normal substances that we know exist as gases, a lot of those diatomic molecules that we talked about at the very beginning, that are also elements, hydrogen, nitrogen, oxygen, fluorine, and chlorine, they're all gases. O3 is ozone, which is a gas. And then obviously our group 8 on the periodic table there, which are monoatomic gases, which means that they come as ones. So that's all the dotty red guys there are gases on normal conditions. It's a good time to talk about difference between kind of two terminologies, gas and a vapor. A gas is really a substance that will normally be found in the gas phase under normal conditions. And opposed to that is a vapor. A vapor is a substance that is normally found in a liquid or solid phase under normal conditions, but can be sort of converted into a gas. So water is a prime example of that. That's why we call it water vapor. We don't usually call it water gas or anything like that. Kind of sounds funny. But that's why, again, we sort of refer to it as water vapor, kind of like what we collected along with our gas the other day and will today as well. When we kind of heat up that water, we create water vapor that comes along for the ride. So let's talk a little bit about pressure of gases. The major gas in air is actually nitrogen, followed by oxygen. As we kind of go above sea level and increase in altitude, the pressure starts to decrease as well. Why they pressurize, right, planes and all that good stuff when they fly. One of the most readily measured sort of property of a gas is pressure. And we have several sort of units of pressure that we do come across. And these are some very common sort of units. Let's come back. One is an atmosphere, which is an ATM. Also a torr and an mmHg, which are millimeters of mercury. And that is because one of the instruments that we typically use to measure pressure is a barometer. We used to be a pool of mercury, and you had like a nice tube in there. And basically, as the atmospheric pressure sort of exerted on the mercury, mercury would rise. So mercury is an unusual sort of substance. It actually has a meniscus that goes the other way, kind of curves upward. And if you ever come across a mercury sort of barometer, you actually read from the top of the meniscus in that case, as it's kind of a weird thing that it does. Now, we use, obviously, as we did the other day, we have digital ones. We also have one hanging on the wall as well. But these are some important sort of relationships. So a torr is named after the guy who invented the barometer, and mmHg millimeters of, because again, on the barometer there usually was a ruler, And in that ruler, you would sometimes measure in inches, centimeters, or millimeters, basically mercury. So basically taking like a ruler reading of the mercury on the column. So that's where those units come from. A torr and a millimeter of mercury are equivalent to each other. It's a 1-to-1 conversion, which means if you need to convert between them, you just change the units. And 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. So you do need to know that conversion for sure. It is used a lot. If you have atmospheres and you want millimeters of mercury or torr, you need to multiply by the 760. And again, that gives you millimeters of mercury, which again is the same thing really as a torr. If you have torr or millimeters of mercury, you need to divide by 760 to get to torr. I'm sorry, to get to atmospheres. And that will give you atmosphere. So that really is an important conversion to know. You use it a lot. I would say probably in most chemistry classes, those are the 3 sort of popular units of pressure that you come across the most, would be torr, millimeters, mercury, and atmospheres. Any questions on that there? Yeah. No, so they use some other, I believe they use more of electronic sort of devices. I'm not 100% sure how the digital one uses it. For example, some other ones use maybe like an alcohol-based one and that type of thing. I'm assuming it's sort of calibrated to like a true barometer or something like that. Yeah. So here's a picture of a traditional barometer. Again, you have this sort of pool of mercury, and then as the atmospheric pressure goes on it, again, you can see the mercury meniscus going the opposite way than a normal meniscus when we look at it. Some other units that we also will sometimes see, I would say occasionally, not a lot so much in chemistry, are pascals and kilopascals. That is sometimes seen. Not a tremendous amount. There are obviously other units of pressure like PSI, which is pounds per square inch. There's also units of pressure which are referred to as a bar. A bar in an atmosphere is pretty close to each other. It's like 1.01 to 1, sort of the conversion between them. They're pretty close to each other. In terms of Now, when we talk about gases, we see a number of different gas laws. For a lot of gas laws, they pretty much use these 3 variables: pressure, volume, and temperature. So these are 3 sort of variables that we deal a lot with when we're dealing with gases. And a lot of these gas laws will look at these guys. In certain cases, we may keep one constant and vary the others. And in some cases, we may actually just vary them all as we go through it. The first relationship we're going to look at is what's known as Boyles' law. And Boyles' law looked at pressure and volume, and it held temperature constant. So Boyles' law looked at holding temperature constant. And basically what Boyle saw was that as you decrease the volume, so basically if the volume got a lot smaller, that leaves a little bit of an area for the gas molecules to fly around in. And because the volume came down, that means those gas molecules are going to actually increase the number of collisions because they just frankly have a much smaller place to fly around in. So by lowering the volume, it's going to increase the number of collisions, and that will increase the pressure that we see. So basically what Boyle saw was as the volume went down, the pressure went up, and actually vice versa as well. If you were to sort of increase the volume, we would actually see the pressure start to come down. And for the same sort of reason, if you increase the volume, you give everybody a lot more room to fly around in. It's going to take longer for collisions to occur, and thus we're going to have less collisions, and we're going to see the pressure actually go down. So it's sort of an inverse relationship. As one goes up, the other goes down under these conditions. Another interesting sort of factor about sort of Boyle's law is pretty much if you do an experiment, you take a bunch of pressure versus volume measurements. So pressure and volume measurements that kind of go together. You pretty much for that gas can multiply those numbers together and it will equal a constant value pretty much for that gas. And that is what this little K refers to. It's a proportionality constant, which basically means any pressure volume relationship that goes together for that gas will result in the same number. And that's useful for a lot of these gas laws because you could then actually set these guys equal to each other and we get pretty much what is Boyle's law right here. This is P1 times V1 equals P2 times V2. This is sort of a before and after situation. So maybe you change the pressure, maybe you change the volume, and you can figure out how it affects obviously the other sort of factor when you do that. Now, in terms of units here, the pressure does not matter as long as they are the same units on both sides. So as long as they're the same units on both sides, they will cancel out. Same thing with the volume. As long as the volume units are the same on both sides, you can use any volume unit you like. Everything will cancel out correctly. So let's take a look at a graph here. This is a graph of pressure versus volume. And we see what we talked about at a much smaller volume. We have a much higher pressure because the number of collisions are going to increase as there's not enough room for everybody to fly around in. We kind of give everybody a little bit more room there in terms of volume. We see the pressure comes way down. Again, it's going to give everybody more room to fly around in and cause less collisions. All right, so let's try one here. A inflated balloon has a volume of 0.55 liters at sea level, where the pressure then goes to 0.4. What is the final volume of the balloon? So a moment or two, see what you come up with here. Okay, let's take a look. So a lot of times when you're dealing with gas law problems, it's a really good idea just to pull out the information. It can kind of help you choose the right gas laws. So obviously here we have a volume that is 0.55 liters. 1 atmosphere is a pressure. 6.5 kilometers is useless information in this problem. So we have another pressure here that is 0.4 atmospheres, and we are looking for a volume. Obviously, at this point, we only have one to choose from, which would be Boyle's law, which would obviously be the correct one to choose here. But sometimes you do have obviously choices a little later on in this chapter. So sometimes if you lay it out, you could kind of see Boyle's law here as well. You could call the first ones ones, the second ones twos. In this case, the unit wise, we have atmospheres and atmospheres for our pressure, so we're all good. This would then be P1 V1 is equal to P2 V2. In this case, we're going to send P2 to the other side by dividing it over there. And that gives us P1 V1 divided by P2 is equal to V2. Putting in our numbers correctly here, we got P1, which is 0.55 liters. That would actually be V1. P1 would be 1 atmosphere divided by our P2, which is 0.4. Atmospheres will cancel. That's going to leave us our volume here in liters. And in this case, we end up with 1.4 liters in this particular case. It's on that one. Now, understanding sort of what happens, different look at what is going on. 1 atmosphere in terms of pressure, and then we drop to 0.4. So in this case, our pressure is going down, which means we should expect the volume to go up. And that is what we did. 5 liters, and we ended at 1.4 liters. So it's good to understand those concepts of what's going on because it's very, very common in gas law problems that people invert numbers. Yeah, I'm putting the wrong numbers, V1 for V2, P1 for P2, and kind of mix them up. So you can kind of make sure that your answer is when you get there. Okay, that's one we just did. All right, the next one we're going to talk about, a couple gas laws, is Charles Law and gay-lussacs law. And these dealt with a couple of different relationships. Charles Law really dealt with volume and temperature, holding constant pressure. And his gas law was V1 over T1 is equal to V2 over T2. And once again, this is at constant pressure. Gay-Lussac's law dealt with pressure and temperature, and it held constant volume. And that is P1 over T1 is equal to P2 over T2 in this particular case. So let's talk a little bit about each of these sort of gas laws here and what happens and what we would expect to happen in these situations. Let's start with the guy on the right there, where we're holding the volume constant. So if we hold the volume constant, which means my container's volume is not going to move, it is fixed, and my gas molecules are stuck in that volume, basically. When I increase the temperature, would I expect my gas molecules to move faster or slower? You would expect the gas molecules to move faster when you increase the temperature. When you increase temperature, they gain energy. They start flying around a lot faster. So when we would increase the temperature here, we would have molecules that are flying around a lot faster. The volume in that container is not going to move, which means because they're flying around faster, we would expect more collisions to occur. And because we would expect more collisions to occur, we would actually expect the pressure to go up in this case. So they got nowhere to go. They're going to fly around, going to cause more collisions, and we would expect the pressure basically to increase with it. Now, if we do the opposite and lower the temperature here, our gas molecules are going to start flying around a lot slower in that area. Now, because again, the volume is pretty much fixed, they're going to fly around slower in the same volume, which means it's going to actually cause less collisions to occur because they're moving a lot slower. And because we're going to have less collisions, we would actually expect to see the pressure start to go down in this case. So we would expect to see pressure drop as well. Now, over here on Charles' law side here, where we have constant pressure, but the volume is not fixed, that means in this case, the volume of the container could pretty much go up or down, sort of adjust, if you will. And in this situation, if we were to increase the temperature, once again, we would expect our gas molecules to fly around a lot faster because it's gain energy, but we want to keep constant pressure. So obviously on the situation on the right, where the volume doesn't move, we see the pressure go up. So what happens in the way it's able to basically maintain constant pressure is the volume will adjust. So even though our gas molecules are flying around faster, the volume is going to adjust and become larger. And that's going to basically keep the same number of collisions occurring, even though they're flying around faster. They got a lot more room to kind of fly in. So the way it's able to sort of keep that constant pressure is the volume actually will adjust with the temperature. So as the temperature goes up, we'll increase the volume. That will again give everybody more room to fly around in, maintain the number of collisions, and keep the pressure constant, which is what we have going here. Opposite is true here. If we lower the temperature, what's going to happen is, again, our gas molecules are going to fly around slower, going to lower the number of collisions. And again, we would typically see the pressure come down. To fix that, what happens with the volume is the volume comes down. So the volume comes down. So even though they're moving around slower, they're still going to be able to maintain the same number of collisions and keep it at constant pressure. So the volume will come down here as well. So that is basically how in Charles' law that we're able to pretty much maintain constant pressure is the volume is able to adjust to allow the number of collisions to remain relatively constant and keep the pressure constant. That again does not happen on the right there because the volume is fixed. There's no helping it. Once you kind of play with the temperature, it is going to directly affect basically the pressure of that system. Any questions on that there? Now let's talk about a couple important aspects of this here. We'll take a look at this graph here. if you graph volume versus temperature for any gas that you like, and you extend their lines back to the temperature axis there, it will all hit the exact same spot, which is minus 273.15 degrees Celsius, or very bad Celsius there. That number should look familiar to you because that's the number we use to do what? Convert to Kelvin, basically, yeah. And Kelvin recognized that and said, you know, if we add 273.15 to convert to Kelvin, that gives us 0 Kelvin, which is absolute 0. So Kelvin recognized this sort of nature of this relationship in terms of temperature, which basically means when we look at our gas laws here that we were looking at, pretty much every single time you have temperature, it needs to be in Kelvin. So again, temperature in Celsius plus 273, we'll convert it to Kelvin. It is a no-brainer. Yeah, if you're doing a gas law, convert the temperature to Kelvin. Every gas law to Kelvin. Even questions where they give you the temperature in Celsius and ask for the answer in Celsius. Sometimes people think, well, they gave it to me in Celsius. I want the answer in Celsius. I can convert it. I don't have to convert it, but you do need to convert it. So you got to convert it, put it into the gas law, and then afterwards convert it back to obviously Celsius at the end of it. So pretty safe bet. Temperature needs to be Kelvin. Now, in terms of the other units here, the volume can be really any unit you want. Again, as long as they are the same, so everything cancels out. And again, pressure on the other side there can be any unit you want. Once again, as long as they do cancel out. Any questions on that there? Okay, and that's basically what this says. All right. All right, we will lay it up there.